Inaugural lectures are one of the very few formal events that we have here at Imperial College. An inaugural lecture is an occasion in which we celebrate the accomplishments of the individual, and we celebrate the fact that he's with us. Tonight, we are very pleased to celebrate the inauguration of Alessio. Alessio is from Milan. He earned a laureate in electrical engineering, brackets higher mathematics track, and an MSc in computer engineering, both from the Politecnico di Milano. He then came to Britain, and within 2 years, in 1999, had earned a PhD from Birmingham under the supervision of Professor Mark Ryan, who I have seen here today. There he is, and is an old alumni of Imperial. With his thesis, Knowledge Sharing Among Ideal Agents. Sorry. He then took a tour of the large London colleges with a postdoc at QMUL under Mike Wooldridge and Nick Jennings, followed by one at Imperial with Marek, then to King's for a lectureship, UCL for an SL, and then back to us in 2006. We really hope that his tour has reached its final destination. Okay? In 2008, he was awarded a readership, and in 2011, a chair. Alessio's chair is in the logic for multi-agent systems, and his research concerns the logic-based specification and verification of autonomous systems. An autonomous multi-agent system is a software system where the basic computation units are conceptualized as autonomous agents. That means they have their own goals, and they formulate their own plans, and they do what they want. And we've all been on the web and seen software that does that. He focuses on symbolic verification, applications of verification, and development of formalisms for the specification of multi-agent systems. His work is very well received. For those of us who submit to conferences, we know how hard it is to get a paper accepted at a highly competitive venue. Last summer, Alessio, with his verification of autonomous systems group, had 3 papers accepted at the top conference, ICHCAI. This was held in Beijing, which just gave him yet another trip. I've been told that Alessio is great to travel with, not only because he has good fun, but also his vast travels give him access to all the first-class lounges. I don't want to think about his carbon footprint. If you search his webpage, you will find a plethora of grants. The one I wish to point out is his EPSRC Leadership Fellowship, Trusted Autonomous Systems, which is running from 2011 to 2016. When Alessio had been here for a year, I went to him to ask him to do some administrative task, probably to run the first years or third years or something, and he said, of course I'll do whatever you're going to ask, but the thing you really want is you want somebody who's a research grants facilitator. I have been here a year, and I now understand all the systems for applying for money from Imperial College. And we thought it was such a good idea that, within 2 days you had a new job? And his web pages have been very helpful to people. In our department, he has given numerous people advice and is very appreciated for it. He became Deputy Director of Research, and now he's on the department's REF committee, which anyone who isn't an academic is the most crucial job that all people in academia are doing right now. As to teaching, Alessio teaches a very popular third-year and MSc course in systems verification. My personal tutees have told me it is a wonderful course, and they hope that they will do well enough for Alessio to accept them as project students. I do want to give a special mention to the effects of his first postdoc, which was on a grant called Practical Negotiation for Electronic Commerce. I have it on good authority that Alessio is an expert at getting a good deal when buying on the web. Right? Once, when Alessio was booking a holiday in Thailand, he noticed, and don't ask me how, that there was an error in the exchange rate, and if he bought the holiday in Uganda shillings, he could get it for almost nothing. I leave you to talk to him about what he actually paid for his holiday. Ladies and gentlemen, it is my very great pleasure to ask Alessio to give his inaugural lecture.
Thank you very much, Susan. That's really kind of you to say all those very nice things. So as Susan has mentioned, I grew up in Milan in the 80s. And growing in Milan in the 80s and living there in the 90s was really, really exciting. There was all sorts of arts happening. There was a lot of culture. Theatre was absolutely great. There was a lot of cinema. It was really one of the places to be, particularly in Italy. And out of this thriving culture that I was receiving, I got two key interests in my life, and that's all I was thinking about. One was chess, the other was American science fiction. I'm saying two key interests, but really I was only playing chess. I wasn't doing much else than playing chess. And science fiction was something that I was reading when I was just too tired of playing chess. So this is and the picture is deceiving. And the reason it's deceiving is not because of my hair or because of how lean I look. That's really what I was like before coming to England. I'm this one over here, by the way. The reason it's deceiving is that I was smiling. And in fact, actually, playing chess was anything but fun, as much as I remember. Starting a tournament at 8 o'clock on a Saturday and finishing the tournament at 6 o'clock on the Sunday was really overwhelming. The tension, if you play competitive chess, the tension is really incredible. Forget about the paper deadline. That's really when it crunches you. You have to get a move within the next 30 seconds. That is really a lot of tension. And what was really not pleasing with my situation there was that I really wanted to get to master's level. If you're playing chess, everybody tells you should get to master's level, otherwise you don't really understand the game. And I understood that really I wasn't very good at the game. So I was making some progress in my national rating, but I quickly understood that I was never going to get to master's level. And all these friends here, you can see here, they were all masters at chess, and some of them went on to become stronger than masters. So my idea, in my spare time, I was also studying computer engineering. My idea was that, pretty much like some parents do these days, if I couldn't get to master's level myself, perhaps I could program a chess program that would actually get to master's level. So I started reasoning about this problem. This is the 80s, you see. We didn't have really strong chess programs. And what I understood was that to be able to write a chess program that would do this, you need to be able really to store and analyze a very large number of continuation paths in a game in a symbolic way. And you need to teach a computer to do this. So let me just illustrate this over a minute. This is a very famous game that if you play chess at any point, you will have seen the position. It's a game that Fischer played when he was 13. And so you see that position is already very complicated, but effectively black is being threatened by this bishop, the white bishop. He's also got a hanging knight, so probably what all of us would do is play the queen back to e8, to d8, and then move it to e7, and do something along the king side for the king. What Bobby Fischer saw was that actually if you play this bishop back to e6, then after this bishop takes this queen, you can give check, get this bishop, and actually there is a sequence of 10 moves after that move in which Fischer got a rook, 2 pieces, and a pawn in exchange for that queen. Now, if you play chess, you know that that's a winning advantage. And that's how Fischer, at 13 years old, actually won that game. Now, if you think about it for a second, in a chess position like this, at any possible point in time, you may have something between 10 and 20 moves that are actually possible. Calculating 10 moves ahead means that you're actually looking at working out something like 10 to the 10 possible states for the games. Now, Fischer was very bright, but there is no way that he could calculate 10 to the 10 in his brain in 5 or 10 minutes. Okay, what he was very good at, and all the chess players at master level are very good at, and I've never been very good at, is actually pruning the search tree and understanding that there's some paths that you're not going to explore, but there are some paths in which you're going to go deep and explore. So I had an idea about how to do this in computer terms, and I went to talk to one of my tutees at Polytechnical. And one of my tutees, what I was told was that this was actually rather an obvious way of solving the problem. And actually, if I wanted to do well in computer engineering, I better think of something else to do. Now, that was a bit of a blow because I really wanted to study the computational aspects of games such as chess. And I was also told that there were people already in the US working very hard on computer games. And in fact, these people here are the ones that later on started working for IBM and developed Deep Blue, which beat Kasparov in the 90s. So that was a bit of a blow. And if it couldn't be my first interest, I was hoping that it could be my second interest. Now, my second interest was AI, and doing engineering and AI at the same time seemed a little difficult. But looking around, I saw this subject that was called artificial intelligence, and it sounded a little bit like AI. Now, in AI at the time, in the 80s and the 90s, people were looking at common sense reasoning, effectively, and mathematical techniques to be able to make plans for an autonomous agent. And when I started reading about this, and I was given material to read about this sounded to me to be remarkably similar to the science fiction I was reading in my spare time. So maybe, many of you will have read books by Asimov in the 50s. And in fact, Asimov laid out 3 laws that all robots adhere to in his fictional world. Okay, so the first law says the robot may not injure a human being either through action or through inaction. The second one says that the robots must obey the orders given to it by a human being, except where such orders put conflict with the first law. And the third law talks about protection its own existence, as long as this doesn't conflict with the first and the second law. So what Asimov had in mind is that robots would explicitly reason in terms of these first principles, and any decision they would make would actually be a decision that follows one of these first principles. Okay? And in common sense reasoning, pretty much the approach is not too dissimilar. You have some axioms that you want to incorporate in your common sense reasoning. Okay? So what I started looking at was mathematical logic techniques to be able to, and I did this during my MSc, mathematical logic techniques to be able to incorporate some reasoning into an autonomous system. Now, that was 93 though, and in 93 really we didn't have any autonomous robots. All we had were some mechanical arms. 20 years ahead, this is now 2013, and we are in a world where we have things like these. So we have the technology now, or we're going to have it very soon, where we can actually build things like an autonomous car. So in this picture, you have autonomous cars that can actually navigate by themselves, they can avoid pedestrians, they can negotiate with our autonomous vehicles, and they can take any passengers who are actually sitting back to their destination. Okay? So clearly there's huge potential advantages to using technologies such as this. You can think of ways where you can actually reduce congestion, you can think of all sorts of applications, including automatic delivery. So this is an example of an autonomous system that is actually nearly in production. It will not be too many years before we have the technology, in principle, to build an autonomous car that can actually go around in a street. But there's many other technologies. People talk about assisted living quite a lot these days. So we have small robots that can actually stay in a house and monitor the movement of a person, report on their medicine intake. They can learn from the patterns they observe. They can respond to unusual patterns that they witness. They can monitor the basic health parameters. They can respond to commands and go and fetch an item if the person requests it. Some robots can even help with food preparation. And there is a lot of work, as we know in this department, on emotion recognition. And if you have young children playing with their smartphones, or you've been to Japan recently, you know about all sorts of applications that are actually emerging in automatic companionship. These are only 2 applications, but there is a plethora of possible applications in which we have the concept of autonomy really coming of age and deploying applications in the real world. Now, the way that we like to look at this in academic terms is by following a series of definitions of the concept of agents and autonomous agents that came about in the 90s. And the best cited paper is the one by Nick Jennings and Mike Wooldridge, who are both here today, I'm very pleased to say, where they describe a computer system, where they describe an autonomous agent as a computer system capable of autonomous action that displays a degree of social interaction either with humans or their peers. So you see that the emphasis here is already back in the 90s on rational behavior, but also learning, adaptability, and also tolerance to faults or self-diagnosis as well. So given all this, let me just go back to the title of this talk. Should we actually trust the technology that we're becoming increasingly capable of building? So when I wrote the title of this talk, I thought it would be nice to circulate the talk like we did, and I was sure that some of the people we invited would not be able to contain themselves and write back to me with some suggestion to this question. And in fact, I did get some answers, and some very interesting answers from a number of colleagues. I will not be able to put them all on the slide. I will only give you two that were very short. This is the first one. And this is the second one. So, are my colleagues being very cynical? Of course not. Of course not. The reason they answer in this way is that they are very senior. And once you're very senior, you know a lot, typically. And in computer science, the more we know how things can go wrong. And we've all experienced faults with our computers, and that is why we tend to avoid this technology. And we've seen small faults, but we've seen big faults as well in our lives, okay? So for those of us old enough to remember the Pentium division bug, this was a CPU that was engineered that would actually do mistakes in floating point divisions with relatively small numbers, okay? I'm talking about numbers with 8 digits here that are being divided. So that's not really good if you are building a CPU on which your safety critical system, for example, is relying on. We all know about the explosion of Ariane 5 in '96, again caused by conversion in floating point numbers from one register to the other. But actually, we know of a series of errors in crucial applications that we built. In 2007, a squadron of F-22s being delivered to Japan had a computer crash entirely while they were crossing the time date, nearly causing the whole squadron to come down. And perhaps more recently, you've heard of the massive recall of vehicles done by Toyota Prius, when they discovered that actually the ABS, the system controlling the ABS, was actually interacting and interfering with a hybrid system that was recharging the battery, effectively causing the vehicle not to brake. So we know that correct software is very difficult to engineer, and that is why we are reluctant to embrace concepts such as autonomy. And it's going to be even harder in the case of autonomous systems. Okay? Autonomous systems need to learn. They need to be resilient to faults. They need to employ some degree of rationality. This is going to create behavior that is very hard for us to understand and predict. And if you're talking to somebody like my wife, who's a lawyer, she will say, well, who's actually going to pay the price when things go wrong? Where do the liabilities lie here? If nobody's in charge of this vehicle, who's going to pay the bill if there is an accident? Is it the passenger who's just sitting back and reading his book or listening to music? Is it the manufacturer just because they built a car that had an accident? Is it the certification authority that guaranteed that this car was safe when actually it had an accident? These are very hard questions for us to answer. And yet, at the same time, we have this feeling, or at least I have this feeling, that there may be very considerable benefits in adopting concepts such as autonomy, particularly in situations where we have dangerous tasks that we're now giving to humans to perform, or tasks that are very repetitive. So let me change the question a little bit. Let me ask you, under what conditions would we trust an autonomous machine? Clearly, there are conditions where we'll be quite happy to have an autonomous machine. For example, if you have one of the Roomba machines that go around sweeping floors, unless you have very young children, you will probably be quite happy to have one of these in the house, and you'll be quite content that nothing too bad can happen by having a little robot going around and cleaning the floor. One of the topics and one of the questions that people ask when faced with the concept of autonomy is whether they can regain control of the machine. So for example, if you're sitting in a car and you see that things may go wrong, you may want to take control back of the autonomous car. That's what happens on a plane. The pilots can always regain control of the autopilot. They can switch it off and regain control. So can we actually regain control once we have an autonomous agent? There may be advantages of regaining control in an autonomous agent. Well, regaining control works for you if you're assuming that a human is going to be much better than an autonomous agent at solving the problem you are in. Okay? And that may be the case in a number of cases. However, we're all familiar with the terrible accidents that happen in our roads, in our streets every day, and the number of deaths that we actually have caused by traffic, caused by effectively human errors. It's not necessarily the case that humans are more reliable. Humans do make mistakes. And in fact, humans have been known to ignore the advice of an autonomous machine. Okay, so for example, if you remember the tragic case of the A330 a couple of years back, the pilots stole the plane. Well, there was a sequence of events, but the pilots ended up stalling the plane at high altitude. And they kept in their position of stall, irrespective of what they were being told by the autopilot. They kept shouting, impending stall, impending stall, impending stall. They would just not give control back, and they believed they had assessed the situation correctly where they didn't. So you see I'm moving the ground for that sharp question towards a situation where we're actually evaluating the performance of an autonomous machine. And on what grounds should we evaluate the performance? Clearly, we don't want to decide to adopt autonomous cars, for example, purely on the ground of speed or performance. What we care about is whether in this domain, are they going to be as safe, at least, as the cars that we see in the streets today? Okay? Is the performance in line with what we would expect? So you see that the ground now is shifting to a position in which we are very comfortable in computer science. This is what we do a number of times in computer science. We want to assess systems against specifications. So perhaps we can do something similar in the case of autonomous systems. We can assess them against some specifications. So what should these specifications be? Now, if I look back, at what Asimov wrote in the 50s, and I discussed these laws a moment ago with you, I interpreted them as principles that you would ingrain into your program of the machine, and the machine would explicitly use these principles to decide on what action to take. That's good and well if you can do it, but another position you may take is to say that however you program this machine, as long as this machine actually happens to obey these principles, this is something I'm going to be happy with. So however I program this machine and whatever the underlying technology, as long as these three principles are followed, this is something I'm happy with. Okay? So we're moving from implementing these sort of high-level principles into the program that decides what action to take, into a system where we're assessing a system against a specification. And these are going to be, for example, our specification for the system. So formal methods, this is really where computer science can help. So formal methods is a very successful story in computer science. And we devise mathematical analysis techniques that contribute to assessing the robustness of a system. So the research question for us as scientists becomes, can we use formal methods to assess the correctness of an autonomous agent? And to do this, the line that we took was to use and embrace the technology that started being developed in the early 90s and eventually got the Turing Award Prize to Clark, Sifakis, and Emerson in 2006. The technique is one of model checking, and it goes as follows. We're given a system S and a specification P, and we want to assess whether the system follows the specification. To answer this question, and we want a computer to answer this question automatically, we encode this specification by means of a logical formula, a mathematical formula that I call phi p, and we encode the system with this mathematical notation of MS, and we ask whether or not this system, now encoded in a mathematical form, satisfies the specification phi p. So let me try to be a little bit more precise. What is this MS here? Well, this MS is the computational tree for the system. If you think back of the position that Fisher was analyzing all the possible evolutions of the board given the possible moves in the system. So for that game, the computational tree was all the possible board positions that you could get by making a valid move at every single point in time when the turn was either white or black. And similarly, in normal systems, the computational tree for the system represents all the possible evolution of the game, given the possible actions that can actually be performed by the processes in the system at the time. So each state represents a possible configuration, and this state is going to represent the next configuration following some action. What are these 5 Ps? Well, these are typically formulas written in temporal logic, and we've become very good over the years of representing a number of possible states of affairs you may have on your system. So for example, you may write, I will never get to a faulty state. And in chess terms, you'll be thinking whether you ever get down the path in a position where you get checkmate, or whether you ever get in a position when you capture the black's queen. Or we can write things like every request is eventually acknowledged by writing formulas such as this. And we teach our students that some properties should hold in some protocols and shouldn't hold in other protocols. So one of the properties that we insist our students to consider is something like this. If a request is a resource is requested infinitely often, then at some point in the future it is made available. That's something that I personally teach my students from 9 a.m. to 5 p.m. in the afternoon, except that then I go home and insist to my daughter that if she asks for something more than twice, surely she's not going to get it. Okay? So that is a specification that you may take or may take depending on your point of view, depending on the application that you have in mind. But the point I want to make is that we are very good at writing and understanding temporal specifications now. However, the question is, are temporal specifications going to be enough for our needs of assessing and writing down specifications for autonomous agents? Well, let me just consider 3 specifications that you can actually find when reasoning about autonomous systems. The first one says that if an agent knows that one of its current goals are no longer achievable, then it will drop it at the next tick and begin replanning. Seems like a reasonable thing to do for an agent. Here's another one. Whenever a fault occurs, all agents in the system can coordinate to ensure that within X ticks, they will know what fault it is and will cooperate to rectify within Y ticks. Again, that's a reasonable property to have in some domains. And here's another one. All intentions selected by the agent's planning mechanism are acted upon within X ticks. All the specifications are reasonable in some domain, but what they have in common is that they require some building blocks which are strictly stronger and more powerful than the plain temporal logic. They all require you to have building blocks and primitives that talk about the knowledge of an agent in the system, the coordination that may happen, the intentions that may be selected, the fault tolerance of this system. So we cannot just use plain temporal logic to reason about specifications such as this. So the research question that I set about to try and look at 10 years ago or more was, well, can we use model checking technology, or can we devise model checking techniques to represent efficiently all the possible computation of the system, but verify specifications that no longer talk about temporal properties only, but they are much, much more expressive. Okay, they need to talk about the knowledge, the beliefs, the intentions, the joint abilities of these agents when they're pulled together, the fault tolerance, whether they can diagnose faults, and so on. So the kind of research objectives that we set out to do were to develop logic-based techniques, including model checking, to support rich specification sets that go well beyond temporal logic. And we wanted to implement these and release them as open source so that other people would use them and contribute to this research. And of course, we also wanted to assess them in concrete scenarios and see what performance we will get. So in the next 20 minutes or so, I will give you a hint of what we've been working on for the past 10 years. This little survey is not going to be comprehensive in any way, and it's more for sentimental reason. They're going to pick up bits and pieces of the past 10 years. And it's more representing of the story of this research. So for sentimental reason, I have to bring up this picture because it's the first picture that we had on this line. And this is a line that, in fact, I began here at Imperial College when I was a postdoc with my great colleague, Franco Raimondi, at the time. Okay, so we were analyzing the bit transmission problem. This is what we started from. And the bit transmission problem is a very well-known problem in distributed computing where you send a bit of information to a receiver. The receiver will send an acknowledgement back to you. But crucially, the environment is faulty. So the environment may drop messages during the communication. Okay? So people like Moshe Vardi and Joe Harpen and others in the late 80s and the beginning of the 90s analyzed protocols such as this, including this one, and argued very successfully and forcefully that specifications that involve knowledge are much better suited to represent the properties of the system. So if you were to think about what specification something like a bit transmission problem would have to satisfy, and you were to express it in temporal logic, you would start encoding some sort of knowledge of the system into some sort of temporal primitives. Well, if you have a primitive that talks about what actually agent receiver knows, it becomes very easy to write these specifications. So in this case, I would write that whenever an ACK has been received and the bit is equal to 0, well, then the receiver knows that the bit is equal to 0. And even more, I would write that whenever an ACK has been received and the bit is equal to 0, well, then the sender knows that the receiver knows that the bit is equal to 0. Intuitively, this is exactly the specification you want. And intuitively, this is exactly why the sender will stop sending the bit of information. It will stop sending the bit of information because he knows that the receiver knows the value of the bit. That's exactly the reason. At the same time, you can actually show on the protocol that you will never achieve common knowledge of the sequence of exchanges in the protocol. And this is exactly what happens when we're exchanging text and we're never quite sure whether the other person read the message, either because it's been dropped or he didn't actually read it. And that is why when we are, for example, exchanging messages to go out for drinks, we keep acknowledging each other until we're reasonably sure that we actually found an agreement that we're actually going to go for drinks. Okay? We're always afraid that our latest message has not been read. So in this context, what Franco Raimondi and us did here at Imperial was to devise a mechanism where we would actually explicitly look at all the possible traces in the system. We did this explicitly, and this is the original picture of all the possible paths in the protocol. So this is a very rudimentary technique. We were able to verify the bit transmission problem because it's a tiny protocol. And we were able to scale this technology to this number here. So what this means is that the model that we could, in principle, benchmark was as big as 10 to the 3. So he had about a few thousand states. That's as far as our technique could go. What we also observed, of course, and that's something that's very well known in model checking, is that the state space grows exponentially with the number of variables or the number of agents that you have in the system. So it was paramount to us that we had to think about more sophisticated techniques to be able to represent something much bigger than this. Okay? We didn't want to represent 20 states. Maybe we wanted to represent 10 to the 20 states. Okay? So this is when, at a crucial time in 2003, I actually met a very, very close colleague of mine who I'm very happy managed to come today, whose name is Wojciech Pęczek. And he introduced me to a very interesting concept, which is bounding model checking. So in bounding model checking, we're interested in the following observation. Whereas in the previous technique, we would construct the whole state space, the observation is that there may be bugs or there may be properties you can find that are very easy to find, and actually you don't need to explore the whole state space. Again, if I'm playing chess, there's no point analyzing 10 moves ahead or 100 moves ahead if I have checkmated the next move. All I need to do in that case is analyzing the first possible moves that I can actually make. So in bounding model checking, you restrict the model and you take a fraction of this model and you translate this satisfaction that you want to check, is the property satisfied on this model, into a propositional satisfiability query. Okay? So both the formula and the model are translated in propositional terms. So this means that we're going to get a Boolean formula that we can feed a SAT checker with, trying to get an assignment. So if we get an assignment to this propositional formula, which is now a conjunction, I have shown that if this formula is satisfiable, well, then the formula, the universal formula I'm checking is actually not satisfied in the model. If I don't get that this is satisfiable, I need to make the submodel bigger and try again until I explore the whole model. So by using this technique, this was the first technique that we use where we say the model is represented symbolically. What I mean by this is that I'm not representing the states explicitly one by one or through the variables, but I have an alternative encoding which enables me to represent large sets of states by means of a few propositions. So by using these techniques, you have a lot of benefits. You can find counterexamples very easily, particularly shallow counterexample, that is, events that may happen very, very close to your initial state. You also get benefits automatically from SAT technology. So people doing SAT checkers develop new things every year, and in this technique, you're actually importing the technology from SAT, so you get a benefit from SAT automatically. So by using this technique, which we then worked on for a number of years after this, we were able at the time to verify state spaces of the regional 10 to the 12. This was a huge jump for us. We were moving to 10 to the 3 to 10 to the 12. 10 to the 12 starts being a reasonable number already. However, what we also observed was that it is possible that when you're translating specifications such as this, or the model itself, the number of propositions you need to introduce may grow exponentially. Okay? So if it grows exponentially, at some point, you will find a conjunction that you will not be able to satisfy even with the fastest SAT checker. So we started looking at alternative techniques, and again, with my great colleague and friend Franco Raimondi, and joined by Hong-Yang Koo, we started looking at other symbolic approaches, and in particular one based on binary decision diagrams. So the way this works is that rather than asking whether this formula is satisfied on this model, you label all the states that in this formula is satisfied on the model in this way, and effectively you're checking whether your initial set of states belongs to the set of states in which this formula is satisfied. Now I have to represent this very large set of states. As I said, potentially we wanted to reason about state spaces that are very large, maybe 10 to the 15, maybe 10 to the 20. And so these states, again, are represented symbolically. Now, with Boolean formulas, you can represent states in a symbolic way, but there are alternative techniques to represent more succinctly Boolean formulas. Okay? So we teach, for example, our students to use BDTs. BDTs are decision trees, decision diagrams, which can represent the Boolean formulas. And a key property that BDTs have is that they can be compressed. Okay? They can be compressed in something that we call a BDD, a binary decision diagram. So if I have a Boolean formula for A or B and C, this is the corresponding BDT. But this can be compressed into a BDD like this. Now, BDDs have the unique property, and a very key property, that can be canonical. So once you fix the ordering of the variable, they become actually canonical. And on canonical BDDs, you can do all sorts of operations in a very efficient way. Now, on this basis, this laid the foundation for us to build a model checker for multi-agent systems. So we devised a language in which we would actually model the system, and here I have a very succinct description of the bit transmission problem, where I'm enumerating the state, the actions that can be performed, the protocol, the evolution of the system. And differently from model checkers that were available at the time, not only could we support specification languages that are being used in autonomous systems, but also the model that we were writing was fully distributed. Okay, so I'm really spelling out here the different agents of the systems and the decision-making they're having when they're performing the action. So we had various fairness constraints, various techniques to handle synchronicity, asynchronicity, and so on. So the results that we got were really encouraging, and we were really happy at the time. We could verify state spaces of the regional 10 to the 22. Again, this is a huge jump from what we had before. We're moving from 10 to the 12 to 10 to the 22. Again, 10 to the 22 is a reasonable number. Okay, so we could support all sorts of specification languages, including group knowledge, cooperation between the agents, beliefs, and we really built a toolkit that we put available on the web, and people started using it outside Imperial and in all sorts of places. So we supported the generation of witness and counterexample. That's very useful if you're actually trying to spot the bugs in an application. Still, this wasn't entirely enough. So we always wanted to push this barrier further, and we kept working on techniques that enable us to analyze state spaces that are actually larger than 10 to the 22. I'm just going to mention two techniques very, very briefly. This is work that Hongyang and Mata Kwiatkowski in Oxford did fairly recently in 2009. And the intuition was, rather than using faster and faster CPUs, could we actually distribute the computation for this model checking problem by using several cores in a CPU? Now, if you're familiar with temporal logic and you've seen model checking on temporal logic, intuitively, this is a problem that can be parallelized quite efficiently if you have a multi-core CPU. If you have specifications like agent-based specifications, this is going to be very difficult to do because effectively you need to consider all the possible state spaces of the system before you can compute the sets where a particular formula will hold. Anyway, without giving you the details, we were able to show that actually we can gain an order of magnitude in speed in terms of time that takes to verify a state space of an autonomous agent. And we, as I said, we explored a number of techniques. Perhaps the last one I'm going to mention is abstraction, where we were able to show that actually, rather than working on the concrete system, you can actually work the model checking problem on an abstract system and check the result there. And under some conditions, whatever you derive on the abstract system is something that you can actually import in your concrete system. So in this context, we were able to verify state spaces of the region of 10 to the 25. And at this point, we felt that 10 to the 25 is a reasonable number to have achieved, moving from 10 to the 1 to 10 to the 3 at the beginning, all in, 6-7 years, really. So we started thinking whether or not we could apply this technology to some particular concrete use cases. At the time, I was very fortunate to have been put in touch with Professor Veres, at the time in Southampton and now in Sheffield. And Professor Veres was in touch with the people actually building autonomous submarines at the National Oceanographic Center. And this is one of the submarines that they were building. I think that, if I'm not mistaken, I think they had just lost one of these units, and they were very keen to assess them as much as they could before they would actually let them roam free again. And these things are really autonomous. Okay, so the mothership actually loses contact with the sub. The sub has a mission to fulfill, but it's got lots of things to consider while the mission is being carried out. It's got obstacles to avoid. Sometimes it needs to follow a temperature gradient. So it needs to do its own reasoning to try and achieve some high-level objective that's given in the mission script. So this is really engineering. It's no longer computer science. And the way that people design systems very often in engineering is by using MATLAB and Simulink and Stateflow. So what we did with a colleague of mine here, Jonathan Ezekiel, who, again, I'm very happy to see in the audience, is that we discretized and translated these Simulink models into this input to this model checker, which was called ISPL. So we designed a compiler that would actually translate these designs into ISPL. We translated different modules that actually the engineers in Southampton had programmed to control the sub. They became different cooperating agents. And we verified a number of missions before they were deployed. So when we showed them the result, the feedback we got back from them was along the lines of, we already kind of knew that actually the missions were correct. What we really care about is what happens if there is a fault on the sub. Okay, so they were reasonably satisfied that actually the missions would be correct, but the concern was, well, what if a sensor breaks? Or what if a piece of rubber breaks? What are the consequences there to the integrity of the sub? Are we going to lose the sub? Are the sub going to be able to resurface? Are the sub decide to continue on its own mission? What's the sub going to do if there is a fault? So to address this concern, we devised a technique to reason about fault tolerance on these machines. And so starting from this question that I've described so far, where you want to verify whether a particular specification is satisfied on the model, what we wanted to do was to change the model and create a mutated model that incorporates a particular fault that you want to reason about. So we would inject a particular fault into this model, again by means of a compiler, and create a new program, a new system description that would create the mutated model that would exhibit the fault. Okay, so we're moving from MS to this mutated model M star S, which exhibits the possible fault in the system. And then you want to verify whether particular specifications are satisfied. Maybe you still want to verify whether the sub will resurface under degraded circumstances. But maybe you want to verify something more than this. Maybe you want to verify and analyze whether or not this particular fault will be diagnosed correctly by the automatic submarine. So we consider a number of specification patterns. In the first one, we say, well, whenever there is a fault, eventually somebody in some part of the submarine will know about the fault. They were interested in reasoning about distribution of this knowledge of the fault. So from the fault being distributively known to the fault becoming common knowledge and being able to be acted upon by the various models of the fault. And also we consider specification where actually the submarine is not really able to pin down what is it that is broken on board, but it's able to deduce that there is something wrong, and on this knowledge being able to take some decision about what to do. And lastly, what we wanted to assess was whether whenever there is a fault, actually the subunits in the sub have a strategy. So this is a logical expression to say that there is a strategy for the agents in this set such that the fault can actually be rectified. Okay, so it's a number of specifications that pertained to the robustness of the AUV. So this is what we did. We started from 15,000 lines of code, which we then translated into ISPL. The resulting code consisting of 27 autonomous agents. They would actually exchange messages about the integrity of the sub. They would report status variables. And together, what they were doing, really, they were cooperating to execute the mission. But this includes reacting to possible obstacles and so on. The engineers were particularly concerned about a few faults that they'd seen happen before on the sub, and they wanted to know what happens if there is this on that fault. So we took these faults, we mutated the model, and we analyzed the results. The state spaces that we got were in between 10 to the 10 and 10 to the 15. This is really depending on the fault we analyzed. So really, in doing this, what we thought we'd done was to create a methodology which was fully supported by the tools to assess the reliability and the tolerance to faults for an auto sub such as this. So we will start from a Simulink state flow description. This will be compiled into a description in ISPL. We would then use the tool to inject particular faults with the help of the engineer to be able to assess what happens in case of faults. And ultimately, this piece of code would actually go into the hands of this model checker that I told you about, which is called MCMAS. And MCMAS would return whether or not the specification holds, or it would return that the specification doesn't hold, and in that case, it would give you a counterexample. So in the engineer, with a counterexample, we're able to go back to its design in Simulink and modify it and start the cycle again, hopefully being able to correct the bug. So we were reasonably satisfied with what we found in this use case. However, as soon as we started talking to our colleagues, the impression was that we're moving in the direction where we no longer have only one of these subs. Maybe we're going to have a team of these automatic submarines. Maybe they are cooperating to map a terrain, or maybe in a search and rescue mission, they're all cooperating to find something that they need to find and helping some humans. So this moves us into territory where if analyzing one of these things already takes you, it requires you 10 to the 10, 10 to the 15 states, the state space is going to grow exponentially in the number of units that you want to verify. And crucially, there may be properties that you want to assess which are independent on the number of units you have. You know, you may want to say in a particular situation that irrespective of the number of autonomous agents I have, I'm going to be able to do such and such in this particular scenario. So what this means is that we're moving from a situation where I'm actually giving you and spelling you out exactly the components that I have in the system, to one in which I'm saying, you're going to have a bunch of these robots, and can you actually tell me whether or not, given this bunch of agents that you have in the system, this property is going to be satisfied? So this goes under the name of parameterized model checking. And so, as I said, you want to verify protocols irrespective of the number of agents present. Now, as we know from theoretical computer science, this is an undecidable problem. So it is not possible for us to, or anybody, to devise a technique that will always give you an answer for all the cases that you can present to the system. However, undecidable problems are there for us to carve and find decidable fragments. That's what they're there for. So what we started looking at was whether we could find instances of this where we could actually solve this parameterized verification. And so this is recent work with a colleague of mine, Panayotis Kouvaros, who's also here, where we analyze the notion of cutoff. So a cutoff for a system is a natural number such that if you build a concrete system built out of C components, for example, if C is equal to 2, you have two autosubs like I had before, well, your specification is satisfied on this concrete system with two components if and only if any larger system that you can build with more components actually satisfies the specification. So it's something magical, right? It's saying that rather than checking all the possible systems up to infinity, all you can do is actually check all the possible systems up to the cutoff. Okay? So the question is, how do you actually find these cutoffs, and do these cutoffs exist? Well, the answer is that no, in general they don't exist, but they may exist. And in fact, we devised a test to work out the cutoff of a system if a sufficient condition holds. And the sufficient condition is talking about a simulation relation between the template of the agent and the template of the environment they are working with. So you see here now I have this very satisfying number at the bottom right. I'll move from 10 to the 3 to very, very large numbers. I can even hope that in some cases I'm going to be able to verify state spaces that are completely unbounded, so they are in principle infinite. So what are the conclusions to this research? Well, I started by saying that autonomous agent specifications go beyond plain temporal logic. And the picture I wanted to give you was one in which I wanted to present you the fact that model checking methodologies are being developed to tackle these efficiently, and with some encouraging results. This is not only research that's going on at Imperial, but it's going on in many places in the UK, including Liverpool, and many places abroad and in the US. So the applicability of these results is actually fairly general, and not only can you verify autonomous systems in this way, but it's been applied to security protocols, to verify protocols such as anonymity authentication, and to the verification of synthesis of data-aware services. And the line of work we've been busy with was on artifact-centric systems, which is a paradigm introduced by IBM. So the picture I have is a very healthy scientific community, I think, as I said, not just here at Imperial, but generally internationally, that's constantly improving the results, both in terms of the models that you can analyze and the strength of the specification patterns that you can reason about. So given all this, should we trust our autonomous machines? Well, I think that my esteemed colleagues are wise to be skeptical. It is still the case that in some scenario, notions such as autonomy can create behaviors that are currently very difficult to predict and assess, including by the technology that I've talked about. However, at the same time, the current research shows that in some cases we can assess the performance even of an autonomous vehicle, such as the one that I talked about. And one thing that is quite important to me is to know that actually the pace of this development is fairly high. This is something that I think we forget all too often in computer science. We're moving very, very fast. Even 20 years ago, in all areas of computer science, in fact, even 20 years ago, we didn't have anything like model checking. It was very much at the beginning. And if you ask the people at the time where 20 years down the line, they would have been able to verify state spaces or 10 to the 30, or they would have techniques such as predicate abstraction, I think they would have been very skeptical. If you ask them again 20 years ago whether the latest generation of CPUs were formally verified, such as the i7 CPU by Intel, again, I think they would have been skeptical. But this is where we are now, and this is the pace of our progress as computer scientists. And also, we should note that we already employ formal methods for certification programs. If you look at how you get airworthiness certificates for novel planes, where you have sophisticated autopilots, you will see in the requirements that some of them are based on formal methods. So it is entirely possible to me, considering the pace of development, that while we're not there right now, in the future we will be in the position, perhaps, to certify limited range of autonomous agents, for which formal techniques play an important role. Before this happens, I think my esteemed colleagues are right, and it will be very risky to deploy systems that we do not fully understand. Now, I want to conclude with a personal note. Every inaugural has some personal notes. Let me just conclude with some. Of course, it was a great shame I didn't get a chance to play chess more intensively than I've done. However, it's not until recently that I've actually discovered that what we've been doing for a number of years is really analyzing possible sequences in the state space. And actually, it's not too dissimilar to what you actually do when you're playing a chess game or when you become very proficient at chess. And in fact, it's particularly satisfying to me that actually, in the latest range of work, we're actually able to verify state spaces that are even higher in principle than the state spaces that you would find on a chessboard. Now, to do this, I've met a huge number of influential people that played a key part in my development and education. I'd just like to mention two here. The first one is Professor Marco Colombetti, who at Politecnico di Milano first pointed me to the use of logic in computer science and to reason about autonomous agents. And I'm very thankful for all his advice and all his teaching during my final year project between 93 and 94 in Milan. Second one I really want to thank is Mark Ryan from Birmingham, who took me on to do a PhD for reasons I don't really understand, given how badly I did in my interview. But he taught me incredibly. He taught me everything from writing down proofs to writing down a paper with the beginning and the end, thinking through a research line, asking the right questions. I'm very, very thankful for everything that Mark taught me in those 3 years in Birmingham. I was also particularly fortunate to have a great team of people working with me and contributing so much to the research. And I've learned so much from all of you that I will ever be thankful for everything we did together. I really learned a lot, and all the technical challenges that you brought up and we solved together some, it's really been great. I really had a lot of fun. So thank you all very much for this. So I now have two children, and for the first time I realized how difficult and hard it is to raise children. So perhaps for the first time, I would like to publicly acknowledge and thank my parents for everything they did when I was little. Both my parents, my mother and father, and their respective partners, for everything they'd done when I was little. And particularly, I'm very thankful for a particular occasion on one special day when I was 13 years old, and we went to a shop, and they listened to me and they bought me a Sinclair Spectrum and not the Commodore 64 that the shop assistant was really pushing for. So thank you very much for that indeed. In my travels, as Susan has said, I've been very fortunate to work in really a collection of colleges here in London after I finished my PhD that were really, really terrific. So I really enjoyed working with all my colleagues at Queen Mary Westfield at King's, here at Imperial and at UCL before coming back to UCL. Now, Susan has mentioned I've been here for now 7 years, I counted. That seems like a long time. I still feel like I just joined back. And I think this must be because I'm really enjoying my time here. So I'm particularly thankful for Susan for running the department and Jeff McGee for overseeing everything at faculty level and for running the department before. And all my colleagues here at Imperial for providing really this incredibly interesting atmosphere where we can talk about technical results in all the chances that we have seminars and so on. Lastly, I would like to thank my wonderful wife, Laura, for all her love and all the patience she's had with me for the past 20 years, and particularly in times of difficulty. So, grazie davvero. And thank you all for coming.
Now introduce Professor Mike Wooldridge, who will give the vote of thanks.
Thank you, Susan. Thank you, Alessio. I've never been asked to give a vote of thanks before, so I didn't know exactly what the form was. I should prefix my comments just by saying that I know the real reason that I've been invited today. It's clearly a very cunning plan by Imperial College to sabotage the ref preparations for the University of Oxford. However, I have an equally cunning plan. I actually have a bit of a stinking cold, and I plan to heartily shake the hands of the entire Imperial ref team. Actually, I'm quite glad to get out of the madhouse for a few days. I'm sure everybody involved in that knows exactly what I'm talking about. Okay, so I've never given a vote of thanks before, so I asked my friends and colleagues, what do you think this is? And the most common answer that I got is this is like a sort of best man speech at a wedding. So in fact, we are here to celebrate the marriage, the intellectual marriage of Alessio to Imperial College. As we've already heard, before he decided to settle down with Imperial College, he had some youthful flings with other London universities, actually all of the London universities. But it was, I think, obvious to everybody that knew Alessio where his heart truly lay. And I knew that he would eventually find his way back here and he would now settle down in this marriage from which there is no divorce. Okay, so I've known Alessio a long time. It's slightly scary to know him, to realize how long I've known him. It's basically 20 years. And academia, I now realize, is one of the many strange things about academia is that it's a small community, and people that you meet working for different organizations, you can still be interacting with years and years and years later and still know them really well. If you go and work in a bank, that doesn't happen. I mean, people tend to move around much more frequently, and if somebody moves to a bank and a different bank, you never see them again. But academia isn't like that. We tend to keep meeting one another throughout our careers. And as a consequence of this, we get to watch the grand trajectory of people's careers. And in Alessio's case, it's been a particular pleasure to watch that career grow and flourish. When Alessio and I first met, he told me the following story. Just following through the best man thing, a best man is supposed to tell at least one embarrassing story. So I'm going to tell at least one embarrassing story. Alessio told me when he was young, that what he really wanted to be was an astronaut, as well clearly as being a chess player. But this is not surprising for somebody of our age, if I may include, if I may pretend that I'm about your age. We grew up in the era of Apollo. It was quite normal to want to be an astronaut. So I said to my parents when I was a young boy, how do I get to be an astronaut? And they said, well, you have to study hard at school and work really hard for your exams and so on. But Alessio told me, and he absolutely did tell me this, I'm not making it up, he asked his parents how he should get to be an astronaut, and they told him he had to eat lots of pasta. Very smart parents, clearly. So Alessio told me every day he would be walking home from school and get home with a big bowl of pasta, and the more pasta I eat, the better astronaut I'm going to be. This is absolutely true. That's what he told me. Okay, embarrassing story over. So I say, we've seen. I've had the pleasure of seeing Alessio's career arc When I first started working with him, he was my first postdoc, by far the most successful postdoc that I worked with. We didn't get the opportunity to work together as postdoc and PI for too long because I then went away to Liverpool. And as I wrote on references for him, so important did I regard my relationship with Alessio that it was actually one of the things that made me wonder about whether I should really do this, not having the opportunity to work with him. When we first worked together, we've done a number of papers together over the years, over that 20-year period. I very much hope that we'll continue to do some more in the future. But when we first worked together, I'd only just finished my PhD. This was the first grant. I was tremendously excited. There seemed to be a kind of a third person present whenever we wrote papers together. And Alessio has commented on this, but I just wanted to pick it up as well. We would be writing some technical definition and debating the best way to do this. And I would suggest some bit of notation. And he would say to me, and again, this is absolutely true, he would say, "Mark wouldn't like that." And this happened so often. You know, I was actually tempted to say it. So I said, well, let's just bloody phone him up and talk to him about it. Get him down as an author on this paper. So, Mark, where are you, Mark? I don't see you in there right now. I know how much Alessio valued your intellectual guidance. And you really did. I felt almost like I was being supervised you at some point. So frequently was your name mentioned as the ideal of how one should go about writing proofs and technical definitions. So I can only wish, actually, that I was as good a supervisor as you clearly were. Having said that, I also wish I was as good a student as Alessio clearly was. Students like this, I think we now all realize, don't come around that often. Okay, so Alessio, we're now at the sort of you're now in the absolute sort of peak of your career, and it's tremendous to see what you're achieving. We've seen your scientific contributions presented very, very clearly today, and it was great to see that how our ideas have developed from the 1990s and the many technical contributions that you've made. But I have to say, it's a particular pleasure because I think everybody who knows you will agree, not only are you a very good scientist, you're also an extremely nice and extremely likable individual. And when you see individuals do well that you personally like, as much as I know everybody likes you, it's a particularly pleasant experience. So, Alessio, I'm about done. I would like to simply say congratulations. We sometimes hear that the currency of a professor these days is a bit devalued, that professorships are handed out willy-nilly. I know that is not the case at Imperial College. Imperial College is one of the world's great universities, and to have achieved a chair at Imperial College is a great achievement, but you deserve it. You absolutely deserve it. So on behalf of your friends and colleagues, and I believe on behalf of the university, allow me to offer a vote of thanks for your inaugural lecture. Thank you.